This conference will now be recorded.
Great. Good morning, guys. So we were talking about the training models, and we understood within the scotatic gradient descent, there is batch gradient descent and other areas where scotatic gradient can be splitted further. So we were discussing about the learning rates, importance of learning rates. Again, when you're talking about learning rates and scotatic gradient descent, go back and relate your understanding with the top of the hill to the bottom of the hill and how you are going to come down. That is one approach of it. And the second approach of it is standing on the east and asking the question, how should I go down to the bottom of the hill? And the same way standing to the north and asking yourself, how can I go to bottom of the hill? So this kind of questions and approach are made for the learning rates. If the learning rate is too low, then you may have or you may not have a problem. If learning rate is high, you may have or you may not have a problem. That also depends upon the complexity or the constraints of the model you have chosen or the features you are dealing on that specific data set. So all these theory concepts I have been explaining, they are really, really, really very important. I would sincerely request you to go ahead and understand it. And if you don't understand, feel free to ask me. Okay. So in this one, we discussed about the how do you come to a conclusion that how many iterations should do and how many iterations would give you a right prediction. So what happens is the number of iterations should also be not low and the number of iterations should also be not high. You have to decide on how quickly it is converging or how far you're finding the optimal solution. So this kind of things must be very important. And there is a process called e-tolerance. The very simple logic to remember e-tolerance is nothing but the gradient vector value must always be e-tolerance. This e-tolerance is nothing but it is a kind of the process where the algorithm can be interrupted. Algorithm can be stopped, go back, check the values and come again. That is the break clause you can say within the iteration process. That's all you need to remember. Okay. After this, I explain you about the convergence rate. Convergence rate again, talk about MSC, mean square error. Mean square error, how fast it is reaching to the bottom of the valley. If it is reaching fast, is it converging too much? If it is reaching slow, is it converging very less? That kind of things are very, very important. And now always remember in the convergence rate, if we are dividing the tolerance rate by 10 to have more precise solution, then the algorithm will have to run about 10 times more iterations. Okay, this is the simple logic within it. This diagram explains you about the scotatic gradient descent. So guys, one more thing I want to highlight here. Look at the concepts. We were talking within the gradient descent. This is a gradient descent concept. Within the gradient descent, you have batch gradient descent, scotatic gradient descent, and the mini batch gradient descent. Okay, one second, I messed it up. Okay, and you have a mini batch gradient descent. So why you are going with batch gradient descent? When can you choose batch gradient descent? What is scotatic gradient descent? When can you choose scotatic gradient descent? Mini batch gradient descent. When can you choose mini batch gradient descent? When can you go with mini batch gradient descent? This is all we need to learn. And also, if you know the formula of batch gradient descent, how is the formula made of? What are the parameters that are involved in the formula? And how are they related in the form of learning curve, in the form of iterations, and in the form of normal equation? That's all we have to understand. Once that is done and dusted, you can apply the same flow, same logic, and the same approach for the linearized regular models, ridge regression, lasso regression, elastic net, and early stopping. If you complete this session properly, done and dusted with clear understanding of the flow, logic, and everything, you can apply the skeleton and the structure of your implementation across any of the models within the machine learning. Okay, that is what it is. Now let me jump back to my content. Today the session will be going to be very short and sweet because I have prepared only for 1 hour slides. This hands-on also I have shown you very clearly, and you should be able to do it by yourself because the screenshot is clear and the code is also clear. Now here, Scotartic gradient descent. So now, what is batch? Batch is nothing but work is done in the form of batches. What happens is batch gradient descent works very slow when the training set is very large. That's obvious. The name itself says it's a batch. Batch means it's not real time. It does in the form of chunks and chunks and chunks. Okay, perfect. Now, this batch gradient descent is slow when the training set is large. Very good. This as it uses the whole training set to compute the gradient at every step. The reason why it is very slow is it uses the whole training set to compute the gradient at every step. Okay, if you have 10 iterations, the first step it evaluates across all the training data and computes the gradient descent the first step. It goes to second step, it again calculates the gradient at that step with the whole training data like that. So that is the reason why the batch gradient descent are always very slow. But you may think batch is a small part, it must be fast. No, it is not that like that. The batch gradient descent actually uh, it uses a whole training set. If the it is doing in a batch form, but however within the batch it is doing for the whole training data. It would have been much faster if it is not using the whole training data. If you remember earlier, I told you at one step it changes the value of the vector at one point and keeps the others stable and does the validation. That is for different approach, and this is for different approach. Do not tend to confuse. Take a paper, take a pen, draw a diagram, relate my diagram with the steps I have mentioned on the left side, diagram on the right side, you will be clear. Okay, now that is about batch gradient descent. And scotartic gradient descent is it just picks a random instance. It just picks a random instance in the training set at every step. And this computes the gradients based on the single instance only. The name itself says what it is doing. Whereas your batch gradient descent is doing the computation on the whole training data, but your scotartic gradient descent is doing the gradients based only on that single instance. When it is doing that single instance, it is also picking a random instance, not the full instance also. But within the instance, it may be doing for the whole training data, but it is faster. Now, basically what happens is this makes the algorithm much faster. The scotartic gradient descent makes the algorithm much faster because as very little data gets manipulated at every iteration. When I said every iteration, at every instance. Now, also huge training sets can be trained in the scotartic gradient descent, as only one instance need to be in memory at each iteration. Perfect. So this is what it is. So the differences between batch gradient descent and scotartic gradient descent is batch gradient descent is very slow. The reason why it is very slow is it performs the gradient computation on the whole training set, and it will take quite a long time to reach that stage. Whereas scotartic gradient descent, it is initiating or it is working on a random instance. However, it computes the gradients based on the single instance only. Okay, this is making the algorithm much faster. One second, guys. One second. Yeah, this is making the algorithm much faster. And the reason why it's making faster is a very little data is getting manipulated at every iteration, and also huge training set can be trained. Perfect. This is all. Look at the diagram on the left side. It's very close. You have one inner circle, one outer circle. If you see, if you observe carefully, uh, first circle is first iteration, second circle is second iteration, third circle is third iteration. So if you look at the way each iteration is doing, it is connecting the training instances iteration runs, and it is going to learn from each of the experiment. Okay. Now, scotartic gradient descent further explanation. In here, if you see, you also need to be aware if you remember earlier, I explained you very nicely about what happens if you approach the SGD from left and what happens if you SGD on the right and what happens if you approach from the. When I say if you approach, you may have this Plato here is the noise data. Noise data is nothing but the data which is not clean. When I say data is not clean, you may have outlier data, you may have underfitting or overfitting or whatsoever. Don't worry about it. That's the Plato. Now, whenever you are dealing with I think someone has joined. Kavi. Good morning, Kavi. Thank you for joining. Okay. So instead of gently decreasing until it reaches the minimum, okay, for example, what he is trying to tell you is you are here, okay, and the local minimum is here. For example, let's imagine instead of directly falling from here, instead of gently decreasing until it reaches minimum, the cost function bounces up and down. Okay, this is up and down. Why it is doing like this, and do you get any advantage of doing this? Yes, the advantage is decreasing only on average. So over time it ends up very close to the minimum. Okay, this is very minimum, it is very close. At least here, if I have my linear regression diagram like this, I can understand this is actual. Okay, let me take a different pen, different color. I'm expecting this, but I got this. Some kind of observations you can make, right? But always remember, within the scotic gradient descent, do not directly decrease. See, if you just go and decrease, you're not learning anything. You have to make some attribute combinations and you have to experiment it properly. So as part of it, the cost function should bounce up and down, decreasing only on average. But over time, it ends up very close to the minimum. But once it gets there, it continues to bounce around and never settling around. Okay, this is one of the important thing you need to understand. How that is helping you, how you can relate that concept to your understanding. Very simple. Do not directly start jumping from the top of the hill to the bottom without understanding how much efforts it's needed to reach there. Go one step at a time, see the slope. Go one more step, see the slope. Go one more step, see the slope. At times, the slope may be more deep before you get there. But what are you going to do at that time? That is what it is. Over time, it ends up very close to minimum is because over time, if you keep on doing it, at times you will get very close to the minimum. So you know the importance of local minimum, right? Now, when the algorithm is stopped, the final parameter values are good, but not optimal, as algorithm will never settle down. You may still do some regression testing or stress testing to make sure how soon you can get or how optimal you can get the solution. Now, what happens when the cost function is very irregular? Again, cost function, learning rate are all kind of synonyms. Do not worry. The scotic gradient descent has a better chance of finding the global minimum than the batch gradient descent. This is the beauty of SGD. If someone asks you a question, why are we choosing SGD when the data is very small, when data is coming in the form of a batch? Just tell them SGD has a better chance of finding the global minimum than the batch gradient descent. Perfect. Because the randomness will help algorithm to jump out of local minima. Again, when to reach global minima, when to meet local minima, and what is the difference between local minimum, global minimum, you'll get more deep once I explain you the support vector machines, which is our next module. Now try to understand local minimum is the nearest point where you need to reach the target. Global minimum is the more nearest point where you need to reach the target. But why did you reach local minimum first and then went to local global minimum is the key point here. So the first learning curve takes you to the local minimum. If you stress test it and do more testing, it will take you to global minimum. Okay, that is what it is. Now, if your data is more random, every time if it is random, it will never know, or it will take quite long time, or sometimes you are lucky that you may go there quite faster. That is called randomness when you deal with random data. As randomness is there, the algorithm will help to jump out of local minima. When it is trying to jump out of local minima, it will reach to the global minima. Now, as seen earlier, that randomness in SGD is good to escape from local minima. The randomness, the random data you deal with in SGD will help you to move out of the local minima. But the bad algorithms can never settle at minimum. That's what it is doing. So do not set do not the you shouldn't settle less. You always should do the better predictions. But because of the randomness in SGD, there is a problem. Okay, now how are we going to deal with it? How are we going to deal with it? That is very important. Okay, now here what happens is, look at this three with red points. Because of the randomness in SGD, SGD is good to escape from local minimum, but bad as algorithm can never settle at minimum. So SGD also has some limitations. Now, how do you deal with it? Perfect. How do you solve this issue? To solve this issue, you need to know about simulated annealing. The simulated annealing is nothing but the sugar coated sand of words, the sweet words you use to people. Now, one solution for this one is to reduce the learning rate. Again, remember, if you reduce the learning rate abruptly, you are you are training the model in a wrong way. So don't do that. You should know when to reduce the learning rate, when to increase the learning rate, and what is the standard learning rate. Now, the steps starts out large. When these steps will start out large because your learning rate is reduced. This helps make quick progress and escape from local minima. Perfect, I understand that. Then steps get smaller and smaller. This will help the algorithm to settle at global minimum. Super. This process is called simulated annealing. Simulated annealing is nothing but the baby steps. Have we ever seen infants running straight away? No. They take one step at a time, one step at a time. Slowly they'll feel and then move on forward. So the first step is, it starts out very large, the big one. Again, it starts slowly, slowly, slowly. When you start a big step, that will help to make a quick progress and escape from the local minimum. Perfect. Now, when you are making a slow steps, the algorithm is trying to learn and it is going to settle the global minimum. This process is called simulated annealing because it resembles the process of annealing in metallurgy where the molten metal is slowly cooled down. How many of you know that molten steel, molten metal that is slowly cooling down? Have you ever seen what happens when the metal is cooling down? Slowly, it's a big piece of metal when it is cooling down. How it comes out slowly one by one, a drop or a big piece turning out into small one as one drop is falling down like that. That is called simulated annealing. This is very important. Just understand the concepts right now. We are going to link it one by one carefully. When I link, I'll tell you, boss, that day I told you about simulated annealing. Now I'm using simulated annealing. If you are not aware of these concepts, when you work real time, you will tend to do a bad predictions and assume that you're doing good predictions. Okay. Now, learning schedule. Okay. You have started the data science training. Now, if you don't have a proper schedule, you are messed up. Okay. Now, this learning schedule is nothing but it's a function that determines the learning rate. Okay, for this specific algorithm, for this specific features I have, thus the learning rate should be high or the learning schedule should be low. That is a learning schedule. At each iteration, it is called learning schedule. So what I can say here is the function that determines the learning rate is called learning schedule. At each iteration, okay, at this iteration, your learning rate is small. At this iteration, your learning rate is high. At this iteration, your learning rate is standard. The reason why it can do that one is If it continues with the same learning rate, it is not going to experiment. If it is not going to experiment, it is not going to learn new. If it is not going to learn new, the predictions are never true. Just think like that. Now, for example, if the learning rate is reduced too quickly, again, we may get stuck in a local minimum, and even we are end up frozen halfway to the minimum. That is true. Always understand, guys, the thumb rule is you shouldn't stuck at local minimum, and you shouldn't go to the global minimum straight away. You have to go to local minimum, bounce up and down, and then reach global minimum. Then I'm happy. Now, if the learning rate is reduced too slowly, now understand the logic here. If it is reduced too quickly, you have a problem, and if it is reduced too slowly, you also have a problem. Now, if you reduce it too slowly, we may jump around the minimum for a long time and end up with a suboptimal solution. We halt training too early. So please be very, very careful. Learning rates, the slope of the mountain, and optimal values of learning rates are very, very important. The learning schedules within the learning rate. In this slide, we discussed if the learning rate is reduced too quickly, you have a problem. If the learning rate is reduced too slowly, you have a problem. So please be super smart in that. Okay. Now let's do hands-on. Time for hands-on. How do you implement the scotatic gradient descent? Now let's start implementing it, guys. It's very simple, straightforward. You can use scikit-learn, and I have attached the screenshot and also the you know the results, what happens from it. So kindly go ahead and give it a try. Let's implement the scotatic gradient descent. By convention, we iterate by rounds of m iterations. When you say m iterations, it can be 10, it can be 9, it can be 5, it can be 4. Each round is called an epoch. M is number of instances in the training set. When I say m is a number of instances training set, if you are doing 10 runs, if you have 10 instances, you have 10 iterations, like that. So by convention, we iterate by round of m iterations. Okay, if you are not convinced with my statement, I'm going to show you what I mean. Okay, this is the SGD regressor here. This is the alpha value. This is the average. This is the early stopping is false. Epsilon is 0.1. The learning rate is inverse scaling. Loss is squared loss. Maximum iterations is none. And the random state is none. And here the iteration is equal to 50. Okay, if you see here, iteration is equal to 50. Let me erase all the drawings and show you again. 1 minute. Maximum iterations is equal to none. Number of iterations is equal to 50. Okay, and inter no change. I'm not sure about this. I'll have to find what it is. Penalty equal to none. Power equal to 0.5. Random state equal to none. Okay, what this is telling is this in this scotatic gradient descent I have implemented, n iterations equal to 50, which means I have 50 iterations here. When I say 50 iterations, in this 50 iterations, the learning rate at each round is very important. And each round, what it has learned is called an epoch. Okay. Now, to transform a linear regression, we need to use a scikit-learn. And in scikit-learn, you have an SGD regressor class. However, things are very simple. Go to scikit-learn, from scikit-learn underscore model, import SGD regressor. Once that is imported, what I have done, I initiated a variable and I have assigned the functionality of linear regression to that variable. Okay, now if you have any questions, if you are not clear what I'm talking about, you need to speak with Google Mata. Let's go and talk to Google Mata now. Erase all the drawings, go back to the pointer. You're talking about SGD regressor, right? SGD regressor. See, these are all the parameters that gives you the results. But however, all you need to do is a linear model fitted by minimizing the regularized empirical loss with SGD. SGD stands for stochastic gradient descent. The gradient of the loss is estimated in each sample at a time, and model is updated along the way with decreasing the strength schedule, aka learning rate. I repeat, the statement itself is telling what it is doing. SGD stands for stochastic gradient descent. The gradient of the loss, the angle of the loss, or the amount of the loss is estimated at each sample at a time. Each sample is each iteration. Each iteration is each instance run. And the model is updated along the way. So you have 10 iterations. First iteration at this learning rate, this is the gradient loss. At stage 2, this is the gradient loss at this learning rate. At stage 3, this is the gradient loss at this learning rate. Stage 4, this is the gradient loss at this learning rate. Okay, that is what it is. Now, here, what happens is, let me show you something. See here. Here, what he has taken is, he has implemented the linear model. Again, he has taken number of samples, like we take 50, and he has taken samples is equal to 10, features equal to 5. So when I say samples is 10, you have 10 records, and in 10 records you have 5 features. Okay, RNG equal to random state. Okay, again y is random samples, x is also random samples. Now if you do this model, it is nothing but CLF is classification is equal to linear model underscore regression, max iteration is equal to 1000, tolerance equal to LE minus 3. Again, this tolerance is nothing but I have shown you the European E symbol. Okay, I'll show you that one now. Give me 1 minute, folks. This is the tolerance. When norm of the gradient becomes smaller than the E tolerance, interrupt the algorithm. Okay, you'll understand this practically when we complete the whole, the training models module. This is quite big concept, guys, because we're covering each and every concept. I think I have to prepare 50 more slides. All these days we have done 53, and I think other 50 or 40 slides will come. With that one, we have perfectly completed training models each and every bit. Every concept is related, every concept is linked, and if you don't understand, come back to me. Whenever I say park it, just park it, do not keep that in mind, because we'll relate that concept later. Okay, so this is about the learning, the what we call, this is about the E tolerance. Now let me go back to my Chrome. So if you have any questions, just come here and check what it is doing. This is the output which I've just explained you. And what happens here is, in this one, you are, 1 second, there are a couple of methods it is using. We don't need that methods at the moment, but we need to know about the parameters. Okay, fit linear model with stochastic gradient descent is doing a couple of things. X is your training data, y is your target values. Coefficient initialization is all about the initial coefficients to start the optimization, and intercept initialization is about the initial intercept to start the optimization. The sample weight is nothing but an array-like shape, weights applied to the individual samples. Okay, this is what it is. If you just spend 1 or 2 minutes on this one, you will get a clear understanding on it. If you understand what, see, if I keep on covering each and every small bit, we will never reach our end target. So when I say something that, guys, spend a minute on this one, please do it. You'll connect to the concept more perfectly, because I already done this. I know it very well, but you also have to be learning like how I did it my journey in the starting days. Okay, this is done and dusted, and this also done and dusted. No, we have not done this one. Okay, this is the diagram. So in this diagram, if you observe carefully here, guys, this is my normal equation. When I applied my normal equation, how much I got? I got 4.19. When I applied my stochastic gradient descent, how much I got? This is 4.19. This is 4.17. This is 2.99. 2.9. This is 2.87. Solution is very close to normal equation. What does it mean? So basically, whichever the way you prefer to train your model, you need to know the difference, what normal equation does and what the scotartic gradient descent, the batch gradient descent does. Okay, now look at this 10 lines. I told you earlier, look at these 10 lines here. 1, 2, 3, 4, again. Why these things are very closely coupled and why this one and this one and this one are getting away from the dots? Because at each learning rate, your model is trying to understand what are the optimal values and what are just given values from the output. That is the smartness of it. Hope you are correcting it. Hope you got the concept. In here, the reason why we implemented SGD is we wanted to check if the SGD and normal equation are giving the good results and same results. If it's giving the same results, it doesn't matter whether you used a normal equation to implement the linear regression, or it doesn't matter if you use SGD to implement linear regression, but you should know both the ways so you are smart enough to deal with it based on the situation that you are dealing in the corporate world. Now, let me remove all the drawings. Let me go back to the pointer. Next one, mini batch gradient descent. Okay, the last gradient descent algorithm we are going to look into. Okay, as of now, you understood about batch, you understood about scotartic gradient descent. Now, at each step, what is happening is instead of computing the gradients based on the full training set, as it was doing in the batch gradient descent, or based on one just instance as you did it scotartic gradient descent, the mini batch gradient descent computes the gradient on small random sets. It's very small random sets of instances called mini batches. Okay, let me highlight this for you. This is green, 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 green. Okay, so very good. Okay, this is the mini batch gradient descent that computes the gradient on small random set of instances called as mini batches. Okay, now let's quickly relate it. What happened with batch? What happened with scotartic gradient descent? Okay, so the last gradients descent algorithm we are going to look into is batch and scotartic gradient descent. In batch, what it has done is instead of computing the gradients on full training data set, it did in the batches. What it was doing in scotartic, it just took one instance. Mini batch is more lazy than batch, so it is doing on small random sets. When I say small random sets, it is not even a bigger, larger iteration. It is a random, smaller one. This is called mini batches. What is the advantage you get out of it? The advantage you get out of it is the main advantage of mini batch over scotartic gradient descent is that you will get performance boost, obviously, because it is doing on the random smaller one. Perfect. From hardware optimization of matrix operations. Again, vector and matrix. Hope you have understood. First, it takes a matrix, it applies the transpose of a matrix, and then gets multiplied with the theta. Theta is again a learning curve. A learning curve is again the learning schedule. Learning schedule is again a couple of things we have discussed. Now, it's especially when using GPUs. GPUs are very important. If you speak in the real-time world about your memory and CPU, like that you have GPUs. Very, very important. Less erratic. You get very less error messages in STD, and especially fairly large deals really good in a fairly mini large mini batches. As a result, it goes more closer to the minimum than the HCD. Perfect. Again, one more question here is when it goes more closer to minimum is your local minimum. So don't worry about it. Disadvantage. The disadvantage you get in this one is it is harder for mini batch gradient descent to escape from the local minimum. This is one of the disadvantage, but you can deal with it. Okay. So in the nutshell, we have discussed elaborative on scotartic gradient descent, batch gradient descent, mini batch gradient descent, the advantages of each, disadvantages of each, and how the learning rate differs and how the learning schedule differs, and at each iteration how it assumes the value of the weights and changing it at every schedule. Okay, perfect. Now let me go to next slide. I need to erase all the drawings and go back to the pointer. Give me 1 second, folks. Now next one. If you see here, look at the diagram, guys. Observe carefully. If you understand this diagram, you are done. Red color is quadratic. Green color is mini batch. This is batch. Look at that behavior. It started from here and slowly came here. Okay. This one started here, went up and down, up and down, up and down, and reached here. And this red one is actually targeting the right point. But the behavior model is very important. As we see, for each epoch, as in SGD, each epoch is again each learning rate iteration result. We are creating mini batches from the training set as we did in batch GD. Okay, now let's see the path taken by below algorithms during the training. Okay, all the three algorithms are end up near the minimum. That's what I wanted. All the algorithms always will reach to the end of the minimum, but the approach they have taken, how fast they have come, is very important. Okay, look at this one, all this area here. This is what we wanted, right? Okay, let me erase all the drawings now. I'll show you something. I'll take first, let's focus on I'll take one color, which is pink. So this is all about your guys. Can you see my painting? I'm writing something. I think you can see. I can see that you can see. Okay. This one is about scotatic gradient descent. Okay. Let me change the color now. This is your batch. It started from here and then reached here. But where did the scotatic started? It started here. Why it didn't start here and started here is the internal behavior of scotatic gradient descent. Now look at the mini batch gradient descent. Mini batch is so lazy that even if this started here, if this started here, it started at this point and it reached this point, and they both were intersected at this point. Now this is called the local minimum. Now what about global minimum here? Do not worry about global minimum when your local minimum is more accurate and more standard best prediction you have got. Okay, that is what it is. That is all the drawings. Pointer. That is all the drawings. Okay, now look at this. What are the observations we can make from scotatic gradient descent, batch gradient descent, and mini batch gradient descent? Okay, now one important thing I can say is batch gradient descent path actually stops at the minimum. Okay, let me take a pen here again to help you. Black. Which is batch gradient descent? This one, right? What happened? This is actually stopped at this point. It didn't even care to move further. That's the importance of batch gradient descent. All the three algorithms end up near the minimum. Okay, this one is here, this one is here, and the green is here. Okay, let me erase all the drawings. Let me go back to the pointer. Okay, now what happens here is both batch gradient descent and mini batch gradient descent continue to walk around. Walk around means up and down. Why are they doing it? They are naughty. They just wanted to go and go and just check how what happens if I go a little deep. What happens if I just stay here for quite long? What happens if I stay stubborn and do not want to move further, like that? So the scotatic gradient descent, which is red, is keep on moving like this, and your mini batch gradient descent, which is in green, also keep on moving, but this has stopped at this point. Okay, now batch GD takes a lot of time to take each step. That's what we discussed from the starting of it. The batch gradient descent takes a lot of time. When someone talks to you about stochastic gradient descent, mini batch gradient descent, your mind should have this diagram registered. Tell them, boss, batch gradient descent will stop at one point on the minimum. But stochastic gradient descent and mini batch gradient descent walk up and round because it wants to check the results of different attribute combinations. Now, batch GD takes a quarter of long time at each step. This is also very important. Now, let's understand the differences of each of the one carefully. If we take a pen, the normal equation is fast. The normal equation is fast. It is not out of scope. It is large and it is slow. Hyperparameter starts with 0. Scaling is not required. Scikit-learn is having the linear regression class. Batch GD is nothing but it is very slow. It is not out of core support. It is faster. The hyperparameters will have 2. Scaling is required and it has no class in the scikit-learn. Stochastic gradient descent is also fast. It is out of core and it is very much faster. Hyperparameters will be greater than 2. Scaling is required and this is the class. Now, mini batch gradient descent is fast. It is yes out of core and it has got larger and faster. The hyperparameters is greater than 2. You can use more than 2 get hyperparameters. Scaling is required yes and the class is not available. So what do you understand by this? The scikit-learn class is available only for normal regression, for normal equation and the stochastic gradient descent. But there are projects which have implemented batch gradient descent because the data is accumulative and cumulative keeps coming in. For the new data coming in, if you apply batch gradient descent, that will be good because stochastic gradient descent for streaming data, it doesn't help you anyway because stochastic gradient descent assumes the new data coming in is already trained and it is spoiling the whole learning rate. It's spoiling the whole experiments it is learning from it. That's the importance of your normal equation, pad JD, stochastic JD, and mini JD. And after this, we'll jump into polynomial regression. After polynomial regression, we'll move on to the next step. I think we'll have to finish this concept by Friday, done and dusted completely, so we can move on to the support vector machines. We have 26 days, 27 days left, and within 27 days, I'll finish the concept in 20 days, and last 7 days, I will train you on a real-time models where you will have to do it by yourself, where I will be doing a shadowing for you. Okay. Thank you so much, Kavi, for joining me this morning. I sincerely appreciate all your commitment, patience, and courage. Now, please, 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 as I keep on saying, take down a pen, take down a paper. While you are learning these videos, theory concepts are boring, which I do agree, but please practice, think logically, and make a note of all your observations, make a note of all your questions you have, and speak to me. Thank you so much. I'll see you all tomorrow. Have an enjoyable day. See you. Bye.